Welcome to the class on Applied Computer Vision and Image Processing. Today we will cover stereo vision, epipolar geometry, and estimating homography between images. These topics are covered to the extent that you need to solve your assignments. There are many more details in stereo vision, epipolar geometry, and estimating homography that we are going to leave out of today's lecture. The slides contain links to other tutorials and lecture series where more details are covered. And we will ourselves also cover this in the class if time permits. Stereo vision is the ability to estimate depth using two images. So let's say you have an object and you're taking a photograph of the object using two cameras. So let's say this is camera number 1 and camera number 2, and these are pinhole cameras. The light that is coming from object A onto the imaging plane of this camera is incident at location P1. Similarly, light from object A is incident on this camera at location P2. So you can see that the image of object A is not formed at the same location on both of these cameras. And this difference in the location can be used to estimate the depth, or AC. So we again have this object A which has been captured by these two cameras. Now you can measure the displacement of the object on the imaging plane of these two cameras as D, which is equal to P1 I1 plus P2 I2. Right, so P1 I1 and P2 I2. In the case of a pinhole camera, the triangle ACL1 is similar to triangle L1 I1 P1. And by using elementary geometry, you can say that P1 I1 is equal to L1C divided by AC and multiplied by L1 I1. So P1 I1 is this part. Similarly, elementary geometry also tells you that P2 I2, this distance here, is given by L2 I2 multiplied by L2C and divided by AC. Therefore, P2 I2 is equal to L2 I2 into L2C divided by AC. This corresponds to this part here. The equation can further be expanded to give AC is equal to L1 I1 plus L1 L2 divided by C, where L1 L2 is the distance between these two pinholes or apertures of the camera. It's rather easy to see that AC is now giving you the depth of the object given the disparity D and these parameters, which can be obtained from the camera. Let us look at a different situation where the object appears on same side of the principal axis of both the cameras. In this case, the relationship between the disparity and the distance of the object from the camera is slightly different. So for example, here object A appears on the right side of this camera and on the right side of this camera as well. Now in this situation, the equations of I1 P1 and I2 P2 are obtained like this, and the disparity is computed as a difference between I2 P2 and I1 P1. The disparity, or the difference between the positions of the image of this object, can be expressed as I2 P2 minus I1 P1, which is further obtained as L1 I1 into L2C minus L1C divided by AC, and this L2C minus L1C becomes L1 L2, and therefore you get disparity equal to L1 I1 into L1 L2 divided by AC. So the depth of the object, that is the distance of the object from the camera, which is AC, is obtained as L1 I1 multiplied by L1 L2 divided by D. This is the same as what we had obtained in the previous equation, where the object was present on opposite sides of the principal axis. Let's see, here we obtained the depth or the distance of the object as AC equal to L1 I1 into L1 L2 divided by D. So there are two situations of how an object may be incident on two separate cameras. If the object is incident on opposite sides of the principal axis, the displacement is computed as the sum of these distances. If the object is incident on the same side of the principal axis, like in this situation, the displacement is computed as a difference. But in both cases, the equation to obtain depth is the same. There's only a difference in how the displacement is computed. Let us look at an example to understand how this works. Two cameras which have a resolution of 1600 by 1200 pixels were placed next to each other at a distance of 0.3 meters. That means the distance L1 to L2 is 0.3 meters for these cameras. The cameras were arranged so that they were at a distance of 2 meters from this scene, from this book more precisely. And one set of images have been taken. So image A1 is the image that is obtained from the left camera, that is this camera, and image A2 is the image that is obtained from the right hand side camera. After taking this picture, the camera was moved to a distance of 2.7 meters from this wall, and a second set of images were taken. So you get image B1 from the left camera and B2 from the right camera. If we analyze these images to figure out how this top edge of the book is oriented in these images, we will see that this edge is at a distance of 410 pixels from the left hand side of image A1. Similarly, the edge of the book in this image is at a distance of 164 pixels in image A2. The disparity therefore is 246 pixels. Similarly, in this image B1, B2, the disparity is 184 pixels. Let us assume that we knew the distance of the camera from the wall in scene A, but we do not know the distance of the camera in scene B. So how do we compute the distance of the camera in this image, in scene B? Because we know the depth for image sets A1 and A2, we can compute this equation AC for image A. That means the depth in the case of image A multiplied by the disparity in image A is equal to L1 I1 multiplied by L1 L2 from this equation. So we can get 2 into 246 equal to L1 I1 into L1 L2, because 246 was the disparity and the distance was 2 meters. Now you also know the disparity of images B1 and B2. Let's plug that in. The distance of the camera in the image set B, let it be ACB. So we'll have ACB multiplied by the disparity in B is equal to L1 I1 into L1 L2, again from this equation. The disparity in the case of these image sets B1 and B2 is 184 pixels. That is ACB, that is the depth in image B, multiplied by the disparity in terms of pixels, that is 184, is equal to L1 I1 into L1 L2. By substituting the value of L1 I1 into L1 L2 from this equation into this, we obtain the depth of the object from the camera in the images B1 and B2. And this depth is obtained as ACB equal to 2 times 246 divided by 187, and this happens to be 2.67. This is the estimated depth that we have obtained by using the displacement or the disparity equations. The actual depth of the camera or the actual distance of the camera from the object is 2.7 meters. So we are not that far away from the mark. So the result that we got was 2.67 and the actual value is 2.7 meters. So using the displacement equation, you would be able to obtain the distance of objects from a camera. Using the concept of stereo vision, given a set of images, for example this set A, image A1 and A2, where you know the distance of a specific object in the image from the camera and you also know the disparity of that object, you can use this equation to determine L1 I1 into L1 L2. This value of the numerator can then be used to determine the depth of other objects in other image sets. So for instance, in this image set B, we were able to determine what is the distance of this particular object from the camera. However, there are issues that one needs to watch out for. Variations in the disparity can also lead to errors in measuring the depth. So disparity needs to be measured carefully. Identifying corresponding points is an issue, and that also can cause errors in measuring the disparity, which in turn will change the depth. The method assumes that cameras are identical. This may or may not be the situation. You will need to calibrate cameras to determine that the camera parameters are not changing over a period of time. Any change in the camera planes or distance between the cameras, that is this distance L1 and L2, can lead to a change in the disparity and therefore lead to errors in measuring the depth as well. There are some other options of obtaining depth from a scene. One option is structured lighting, a specific pattern of light. For instance, you can see a red dotted pattern being projected on this wall here. This kind of pattern can be used to determine what is the depth of an object. If a regular pattern is placed on a wall and there is an object in front of the wall, then there would be some distortion in the pattern. And this distortion can be used to measure the depth. Time of flight can also be used to measure depth. A time of flight camera is a camera where light of a specific pattern is transmitted at certain intervals. The time taken by the light to return back to the sensor is measured. This, for example, is a Kinect sensor. It's a Microsoft Kinect sensor that used to be sold with Xbox, and this was very good at measuring depth. Why is stereo vision used when you have other options like structured lighting and time of flight? Structured lighting and time of flight need active light sources. These light sources may need to be really bright. For example, in the case of structured lighting, if there is an external light source which is already incident on the object, then the structured light has to be more brighter so that the camera can see it clearly. In general, because you need an active source, structured lighting and time of flight would end up consuming more power, and this could be an issue in certain use cases. If a certain level of accuracy is required from any computer vision system, then some self-calibration and correction for errors would need to be regularly performed. That means if you are estimating depth and you need the depth to be accurate up to a certain level, then you'll need to self-calibrate and correct every once in a while to ensure that, for example, the cameras are at a certain distance. So in stereo vision, you need to ensure that the cameras are at a specific distance from each other. You also need to ensure that the cameras are perfectly parallel to each other. The image planes are parallel to each other. There are similar conditions in the case of structured light patterns and time of flight as well. Checking to make sure that these conditions are satisfied in the case of structured lighting and time of flight systems could be a little bit more difficult. Stereo vision relies on individual pixels to give depth information. So in general, it is possible that you may get better resolution from stereo vision. And yeah, remember, Mars rover also uses stereo vision. The two cameras that are mounted here, they are stereo cameras, and stereo vision concepts are used in order to estimate the depth of objects around the Mars rover. Let us now look at epipolar geometry. We have previously discussed that in order to form an image of an object on the image plane, 4 coordinate systems have to be understood. The 4 systems are the world Euclidean coordinate system, which depict the location of any object in the real world. The second is the camera Euclidean coordinate system, which uses the camera focal point as the origin. Next is the image Euclidean coordinate system, which uses a point on the image plane as an origin. These coordinates are based on how the sensor array is arranged inside a camera. Images that are used in computer vision are in the form of pixels. These pixels are the final result of the image acquisition process, and they reside in the image affine coordinate system. The pixels are obtained on how individual points are arranged on the sensor array. Transformation of the world coordinate system, that is the coordinates x, y, z, into pixels that are used in image processing is given by this transform matrix. We will now study how the transform matrix is obtained. The transform matrix contains three parts. One is the world Euclidean coordinate system to image Euclidean transform matrix. This converts the world Euclidean coordinates into the camera Euclidean coordinates. The next one is the transform matrix that converts camera Euclidean coordinates into image Euclidean coordinates. This is also known as the perspective projection transform. And the third one is the one that converts image Euclidean coordinates into individual pixels. Let us look at how lens parameters allow us to obtain the position of a point on the image plane, given a point in the real world. Let us say x, y are object coordinates in the real world. These coordinates can be transformed into the image plane in the following way. This x dash, for instance, the height of the object is the same as this height. Now this triangle and this triangle are similar triangles. Using the similarity property, you can determine that x dash, that is the coordinate of the object in the image plane, is given by the equation f of x divided by z, where f is the focal length of the camera, x is the coordinate of the object in the object plane, and z is the distance of the object from the focal point. Similarly, the y coordinate of the object can be obtained as y dash equal to f y divided by z, where y is the coordinate of the object in the object plane. In the simplified case of a pinhole camera, the principal point is considered as the origin of both the camera Euclidean coordinate system and the image Euclidean coordinate system. Therefore, while transferring a point or transforming a point from the camera Euclidean coordinate system to the image Euclidean coordinate system, you would get a negative sign like here. UC dot is equal to minus fx divided by z and minus fy divided by z. The image Euclidean coordinates may also be measured against a different location. So they may be measured from the top left or the top right corner. This can be modeled as UC equal to minus f into x divided by z plus cx, where cx and cy are the translation parameters that are required to move the origin of the image Euclidean coordinate system. The image Euclidean coordinates can be converted into image affine coordinates by applying an aspect ratio, where k and l is the aspect ratio that is applied on the x coordinate and the y coordinate. And finally, the values xi and yi, which you get from here, would be the row and the column in the image that is obtained after the entire image acquisition process. There is a nonlinear term 1 by z in the equation of the image affine coordinates. Let's see, here we have minus fx divided by z, and here we have minus fy divided by z. Therefore, this cannot be easily expressed in matrix terms. In order to express this in matrix terms, we use homogeneous coordinates. Using homogeneous coordinates, we get ui equal to xi yi 1, which is equal to minus kfx plus cx multiplied by z minus lfy plus cy multiplied by z. And then you get the z term here. This is equivalent to ax plus cx z by plus cy z, where we have taken minus kf, small kf, to be a and minus lf to be b. Now this can be expressed in a matrix fashion using this equation. So your homogeneous coordinates xi yi 1 is equal to this matrix multiplication, which can further be represented in the following form. Note that x, y, z and 1 are your camera Euclidean coordinates. K is equal to this matrix, which is also known as the intrinsic parameters of the camera. Now xi here would correspond to columns of your image that you finally obtain from the camera, and yi would be the row that you obtain from the camera. So finally we have the columns, that is xi, and the rows, which are yi, of the image being obtained as homogeneous coordinates here, and they can be expressed as the intrinsic matrix multiplied by this identity and zero matrix here, and then the camera Euclidean coordinates, which are represented by xc. Note that there is a special case of a camera called a canonical camera where K is an identity matrix. In such cases, the row and the column of the camera would be obtained as an identity matrix, which is a 3x4 matrix multiplied by the camera Euclidean coordinates. We still need to transform the world coordinate system into the camera Euclidean coordinate system. The world coordinates can be transformed into the camera Euclidean coordinates by using a rotation matrix and a translation matrix. Substituting this transformation into the equation of ui, we get this equation. And this is further reduced into ui is equal to k times the rotation matrix, the translation matrix, and the world coordinates. And this can be expressed as ui is equal to mxw, where m is equal to k rt. Thus, we have derived this matrix, which allows us to convert from the world coordinate systems into the image affine coordinate system. In this expression, it is shown as h, and here we have derived it as m. You will remember that ui represents the column and the row values expressed in terms of homogeneous coordinates. And this m matrix, or the transform matrix, is made up of intrinsic parameters, which is represented by the term k, and extrinsic parameters r and t. From previous slides, we know that the intrinsic parameters are made up of the camera Euclidean to image Euclidean coordinate transform, and the transform from the image Euclidean to the image affine coordinate transform. And the extrinsic parameters transform the world Euclidean coordinates to the camera Euclidean coordinates. Now let us study epipolar geometry. In order to study epipolar geometry, we will assume that there are two cameras with centers at C and C dash that are observing a 3D scene point X. The projection of this point X is at the location U on camera C, and the projection of X on camera C dash is at the point U dash. The plane defined by X, C and C dash is called the epipolar plane, and the line between C and C dash is called the baseline. And the place where this line intersects the image plane, so this is the image plane for the left camera, this is the plane where the left image is obtained, and this is the plane for the right camera. This is the plane where the right image is obtained. This point E is called the epipole of the image plane of the left camera, and E dash is the epipole of the right camera. And these lines are known as the epipolar lines. Epipolar lines are useful because they assist us in matching of images. Given a 3D scene point that is present at a location U, the corresponding point U dash would be limited and would stay only on this epipolar line. So given a 3D scene point X, if you form this plane XCC dash, you can limit the space where you have to search for the corresponding points U and U dash. And this is useful in matching of images. For instance, when you are doing stereo matching, you want to know where a particular point in image A1 is located within image A2. And if you know the epipolar geometry of the two cameras, you will be able to determine a limited area within which you have to search for the corresponding points. If you did not know the epipolar geometry, you could still match up points in image A1 with points in image A2. You would take the features of the image surrounding this particular point and search for those features all over image A2. But this is a potentially expensive process. If you knew epipolar geometry, you could still use the features and do a search, but the search would be limited to a line. And this would make the search process much faster. We will now study how to relate u and u dash without knowing the camera orientation or the intrinsic or extrinsic parameters of the camera. Now let us assume that all the coordinates in the right hand side camera can be transformed into the image Euclidean coordinates of the left camera with a rotation r and a translation t. So the point u dash, which is the projection of x on the image plane of camera c dash, can now be transformed into the left camera coordinates in the following manner. So u double dash is the coordinates of u dash with respect to the left image Euclidean coordinate system. That is obtained as r transform u dash minus r transform t. With this equation, u dash is now expressed in terms of the image Euclidean coordinates of the left camera. And note that u dash lies on the epipolar plane. U is also a point that lies on the epipolar plane, and this vector RTT, or rather the point that is obtained by applying rotation r on the translation coordinates t, also lies on the epipolar plane. Now because these 3 points are coplanar, you can satisfy this equation. RTT into u double dash, that is RTT and the cross product of u double dash, would be a vector that is perpendicular to the epipolar plane. When you take that vector and do a dot product with u, which lies on the epipolar plane, you get a 0. So that's this expression here. When you expand this cross product, you'll get RTT cross RTT, and the cross product of a vector by itself is 0. Therefore, this expression within these brackets resolves to RTT cross product with RT u dash transpose, and a dot product with u is equal to 0. And you can further expand this to get this expression. The rotation matrix, which was in brackets here, has come out, and it is this 3 by 3 matrix. And u, which is the projection of point x on the left image plane, is a 3 by 1 vector. It's got 3 rows and 1 column. The term here that is left within this bracket on which the transpose is applied is a cross product of 2 vectors. This can be expressed as a cross product of a matrix with a vector, and the details are shown here. At the end we get these 2 equations, and E is called the essential matrix, which is the transpose of this Tx multiplied by the rotation matrix R. Why is this equation useful? This equation is useful because it will eventually allow us to match coordinates that are obtained in one image plane with coordinates that are obtained on the other image plane. Notice that u dash and u are still expressed in terms of the respective image Euclidean coordinates. So u dash is expressed in terms of the image Euclidean coordinates of the right image, and u is in terms of image Euclidean coordinates of the left image. Now the image affine coordinates of the camera can be modeled as follows: ui is equal to k I0xc. In the case of a canonical matrix, the intrinsic parameters k can be replaced by an identity matrix. Therefore, we have ui is equal to the identity matrix, the 0 matrix, multiplied by xc, and this can further be written in the case of this set of points as ui is equal to identity 0 u. Similarly, for the right hand side camera, we'll have ui dash equal to identity matrix 0 and u dash. If you substitute these two expressions in equation 1, you get this result. U dash of I transpose multiplied with the essential matrix and multiplied by ui is equal to 0, where ui dash and ui are the image affine coordinates of a point x, 3D scene point x, on the right and left camera. You will remember from our previous discussion that the image affine coordinates are giving us the column and row values of individual pixels. Therefore, if we know that the camera is looking at some object in the scene and we want to identify a given pixel ui, which pixel does it correspond to in another image, we will be able to use this equation to limit the coordinates of ui dash. In the previous slide, we had made an assumption that the cameras were canonical. In the general case, cameras are not canonical. So the constraints were obtained as u dash transpose tx transpose ru equal to 0. This was equation 0 that we had derived a couple of slides ago. This was equation 0. And we reduced this term in middle to the essential matrix. In general, cameras are not canonical. The camera Euclidean coordinates can be transferred into image affine coordinates using this expression. ui is equal to k, where k is the intrinsic parameter, I the identity matrix, zeros, and xc, which are the camera Euclidean coordinates. And this can be written in the following manner for the left camera. Right? ui equal to k, identity 0 and u. Now u can be written as u equal to k inverse of ui. Similarly, for the right hand side camera, we'll have u dash is equal to k dash inverse u dash. Substituting these two values in equation 0, we obtain the following expression. This can be further reduced into equation 3, where ui dash transpose f, which is a 3 by 3 matrix, multiplied by ui is equal to 0, where ui dash and ui are the image affine coordinates. That means the pixel coordinates of a 3D scene point x on the right hand side and the left hand side camera respectively. And f is the fundamental matrix. Given equation 3, two questions arise. How do we use the fundamental matrix f? And the second question is, how do we compute the fundamental matrix f? We have already spoken about how to use the fundamental matrix. Let us briefly discuss that once again. One of the main uses of the fundamental matrix is to speed up image matching. For instance, let's say for stereo vision, you want to match points in one image with points in the other image and identify correspondences. The normal process is to take a point in one image, extract image features at that location, and match the image features with all the points in the other image. A comparatively faster approach is to take a point in image A1, for instance, identify what are the corresponding locations in image A2 that satisfy this equation, equation number 3. It turns out that according to epipolar geometry and according to equation number 3, if there is a point on a left image plane that you have selected, the corresponding points on the right image will lie on a line in the right image. This limits your search option only to a line as opposed to searching through the entire image. Once you obtain coordinates that are possible search options, you then take features around the point in image A1 pass through the line that you got in image A2, and using these image features as a match, obtain a refined result. Thus, epipolar geometry helps you define this equation number 3 and reduces the search space of a point in one image to a line on the other image. And this makes searching for correspondences much faster. Now let us look at how to compute the fundamental matrix. In the general case, the fundamental matrix is expressed in the following way: ui dash transpose multiplied by f, which is a 3 by 3 matrix, multiplied by ui is equal to 0. Assume that you know the coordinates of two such points. So ui dash is x dash y dash, where x dash is the column value in the right image and y dash is the corresponding row value in the right image. And ui is equal to xy, which is the coordinate of the point that matches with ui dash. And f is this 3 by 3 matrix. Substituting these values of ui dash, ui and f in equation 3 will give you this expression. Now, equation 4 has 9 unknowns and it can be solved if we have 8 points that correspond to each other. This can be represented in the following way: wf equal to 0, where w is a representation of those 8 points and f is this matrix which has been represented as a vector. We can further express wf in the following manner: it's a multiplication of an 8 by 9 matrix with a 9 by 1 vector, and this equates to 0. You can find 8 corresponding points, but several more points can also be used in order to eliminate noise and find a much more refined value of the fundamental matrix f. When several points are used to identify the values of the fundamental matrix, singular value decomposition can be used to find a better estimate of f. Now, how do we find these corresponding points? Like we said that we need 8 corresponding points to satisfy this equation, right? How do we find those 8 corresponding points? These correspondences can be found by either using images with markers. So for instance, these are 2 images taken with 2 different cameras, and these black and white sheets of paper can be manually marked with correspondences. So for example, you could have ground truth which says that this particular coordinate is the same as this coordinate. So you would actually have a human being annotate these 2 points being corresponding points. Similarly, somebody would write down the xy coordinate or the row and column of this point and say that this point corresponds to the row and column of this point in this image, and so on and so forth for every point. So for instance, this point, the row and column of this particular point would correspond to the row and column of this point. And by selecting several such points, you would be able to use these in singular value decomposition, solve for this equation, and obtain an estimate of f. You can also use feature point matching to identify locations that correspond to each other in 2 images. So for example, here we are showing shift points, and the features around shift points can be used to match and identify sets of 8 points that correspond to each other, and these 8 points can be used to obtain the fundamental matrix. You can also have several points that are matching, let's say 50, 100, 150 and so on, and these points can be used with singular value decomposition to obtain an estimate of the fundamental matrix. A point to be noted that image coordinates have very large values. So it depends on the resolution of the image, but in general, having values in the range of thousands is not uncommon. So for instance, this pixel has a coordinate of 1187,460, and when you express it in homogeneous coordinates, you would write it as 1187,460,1. Similarly, this point has a coordinate of 361,10421. So these large values make the computation of SVD inaccurate. So generally the image affine coordinates or the row and pixel values in an image are normalized by taking the center of the image as a region and scaling all the row and column values between a small range. So for instance, the row and columns might all be normalized to be between plus or minus square root of 2. Let us now discuss estimating homography from one image to another image. The homography matrix allows you to transform image affine coordinates of one image to image affine coordinates of a different image. So for instance, if xi dash, yi dash and 1 represent the image affine coordinates of our right image that we have been discussing so far, then this can be transferred into another image affine coordinates xi, yi, 1 using this matrix. And you can consider xi, yi to be the columns and rows of the left image and xi dash, yi dash to be the columns and rows in the right image. Before we go into the details of deriving this homography matrix, let us examine what are the uses of this transform. This transform can be used in applications such as image stitching. Let us say you have a set of images and you want to stitch them together to create a mosaic. Now you need to be able to figure out how to transform one image into coordinates that match up with the other image. Yes, you can do invariant feature point matching to figure out which are the corresponding points, but still you have to take points in one coordinate system and transform it to points in the other coordinate system. This can be done by using this homography matrix. Same goes true for this use case, which we have discussed earlier. This is a reference printed circuit board and we want to match it up with this test board. In order to do that, we need to predict where a particular coordinate in this board will fall on this board. This will allow us to line up the two boards together and identify any differences between these two boards. So if you know the homography matrix that can convert the coordinates of the reference board into coordinates on the target board, we will be able to substitute, for example, the location of this particular component into xi dash, yi dash and obtain the location of this component on the target board as xi, yi. Now let us again go back and consider our epipolar geometry. Transformation from the world Euclidean coordinates to the image affine coordinates can be represented using this matrix formulation. And when you expand it, you get this result. Now in order to get the homography matrix, let us make certain assumptions. The first assumption is that all the points that we want to transform are on the right image plane. This is a valid assumption anyhow, because we want to transform one image to another image. So why worry about points that are elsewhere? We should consider only points that are on the right image plane. And let's figure out how to convert these or transform these points into the left image plane. The second assumption is that the origin of the world Euclidean coordinate system is on the right image plane. And the third assumption is that the z-axis of the world Euclidean coordinate system is perpendicular to the image plane of the right camera. Due to assumptions 2 and 3, the z coordinates of the points that you are interested in, that means all the points that are on the right image plane, become zeros. So what we can do is, in this matrix formulation, we can get rid of all the entries that correspond to the z coordinate. Once we do that, we get this matrix result, which further reduces to our homography matrix, where xi dash and yi dash correspond to points or coordinates in the right image plane, and xi, yi are the image affine coordinates on the left image plane. The intuition behind the assumptions that we have made and the change from these coordinates, the world coordinates, to coordinates on the right image plane is that we are observing the world coordinates from the left camera. The parameters that we have used, the k, r and t parameters that we have used, will account for world coordinates irrespective of what space they are in. So it doesn't matter whether the world coordinates have been measured in millimeters or pixels. It also doesn't matter what is the axis and the origin that we are selecting in the world coordinate system. Even if they are on the right image plane, the k, r and t values will account for those, and they will be able to transform these coordinates into the left image plane coordinates, and which is the result that we have obtained here. We have now shown that transformation from the image affine coordinates of the right image to the image affine coordinates of the left image can be expressed in the form of this homography matrix. Now you can consider xi, yi to be the columns and rows in the left image, and xi dash, yi dash to be the columns and rows in the right image respectively. You need to be aware that these are homogeneous coordinates though, but you can consider them to be equivalent to columns and rows. Now how do we obtain this homography matrix H? This equation 5 has 9 unknowns. In order to obtain these 9 unknowns, we need 8 equations. Now if you take 2 images and you find out corresponding points between these 2 images, right? So for instance, we are using the PCB use case again. This is the reference board that we want to match up with the target board. And if you know that there are 2 points that match up, so there's a point here in the reference board which is matching up with a location in the target board over here. You know their xy coordinates. Then when you substitute these pair of xy coordinates in equation 5, you will get 3 equations. If you get 3 such pairs of points, so that means if you get a point from image, the reference image, let's say you get this point, and let's say this point. And you are also able to identify the 3 corresponding points in the reference image. Let's say this point, and this point. You would be able to plug in these coordinates into equation 5 and obtain sufficient number of equations that will be able to solve for the values in the homography matrix. So getting 3 such pairs of points will be enough to solve equation 5 and get the H matrix. In practice, many such points are identified using invariant feature point matching. So you may have hundreds of such points matching with each other, and these corresponding points are used in a technique like ransack to find the best homography matrix. To summarize, we studied stereo vision, where we understood how to identify the depth or the distance of an object from the camera given its displacement or disparity in 2 different image planes. We also studied epipolar geometry, which allows us to define a fundamental matrix. Using the fundamental matrix, given that we have a point in one image and we want to find the corresponding point in another image, then we don't have to search for the corresponding point in the entire second image. Using epipolar geometry and the fundamental matrix, we will be able to identify a line on the second image on which the corresponding point must lie. So the search space gets significantly reduced to identify correspondences, and the correspondence matching problem can be made much faster. We also studied how to estimate homography, which allows us to convert the image affine coordinates of one image into the image affine coordinates of another image. And we also studied how this is useful in applications such as image stitching. Thanks everyone, hope you liked the class. Looking forward to seeing you in the next lecture. Enjoy and have fun.